Okay, here we go. Let's talk about some derivatives for trigonometric functions. So you probably have seen them as a table or a list somewhere in your math notes. We have the derivative of sine and cosine. First, the derivative of sine is equal to cos, and the derivative of cos is equal to negative sine. Then we have the derivative of secant and cosecant. These are interesting. The derivative of secant is just secant times tan. So it's kind of like it copies itself. And there's a nice pattern with cosecant. It follows a similar style with the negative sign and cosecant by cotan. Finally, we have the derivatives of tan and cotan. These go together nicely because the derivative of tan is secant squared and cotan is the negative of cosecant squared. Okay, I think we can do about 4 examples here and just practice this out a bit. You should see questions similar like this level to your textbook or homework questions. Okay, let's start off with the derivative here of this power of a function. In this case, we have sine x raised to the power of 5. We can take the derivative of the outermost function by the chain rule and have 5 by sine x all to the power of 4. And then take the derivative of whatever's inside the brackets, which in this case is sine. So the derivative of sine is cosine, and there you have it. Let's move on to the next example. In this case, we have the derivative of a trigonometric function and also power function. Let's take a look and see how we can put these together. Well, it's as simple as just finding the derivative of each of these separately. So let's try that out together. So we have here the derivative of tan, which from the previous stated rules is equal to secant squared, and the derivative of x cubed, which is 3x squared. And there you have it. Hopefully nothing too dangerous. We can move on now to the next example involving, a quotient rule. So how do we approach this? Let's try this out together. We begin by finding the derivative of the numerator. And before I actually get that derivative, let's write down a template like we did in an earlier video discussing the quotient rule. So the derivative of the numerator is cos, and then we just copy the denominator, copy the numerator, and the derivative of the denominator is negative sine. Now I'm getting a little bit lazy there by not saying sine of x, but when you do enough trig identities in your life, you end up just kind of simplifying how you write it. I'm going to shrink that a little bit because this looks like it's going to involve a few extra steps here. Now, in the numerator, we can see that if we expand this out, hopefully there is some trig identity that we could take advantage of. Now here we have two negatives. So two negatives multiply to make positive. So that'd be positive sine squared x. And there you have it. You see that the numerator, we can take advantage of the Pythagorean identity. That is, if I just move that sine squared over here, we know that cos squared plus sine squared, well, that's equal to 1. And then if you notice further that the denominator is the square of the numerator. I'm just going to work here sideways because I'm running out of space. So what you can do is you can cancel the numerator with the denominator at one level and just get cos x plus 1, which is the final answer. In this next example, we have a radical function whose radicand involves a trigonometric function secant squared x plus 3. Now, you recall that I did give a shortcut for square root functions in an earlier video as such. Let's apply this pattern to the example here on the outermost layer, which is to do 1 over 2 by the square root of that radicand. So in this case, that'll be secant squared x plus 3. Now we have to deal with the derivative of the stuff inside the radical. Recall that secant of x squared can be written a couple different ways. We're going to use the latter here, secant x all squared, and apply the power rule to that. So in this case, we would have 2 by secant x to the 1 by the derivative of secant x, which is, of course, secant x tan x, as per the cover slides of this video. Almost there. We can cancel out the 2 here and the 2 there, and ultimately write a single fraction to represent the final answer. I'll just copy that over there, and then we just have to simplify the stuff here. So we have secant x appearing as a square, multiplied by the tan of x, and that represents the final answer.